So before we get into quantum mechanics, I just wanted to do a little bit of math review. And on this video right here, we'll just go through complex numbers. So complex numbers usually have the form, we usually call it a z for the complex number right here, and it usually has this form a plus ib, where I is the square root of -1. Now, if we look at all the real numbers, let's just say this is all the real numbers. All the real numbers are also complex numbers. The complex numbers are just a bigger region right here, complex. So all real numbers are complex numbers, but not all complex numbers are real numbers. We call this number right here, A is the real part of Z. And we call B the imaginary part of Z. Sometimes instead of calling these complex numbers, they also call them imaginary numbers. I assume the reason why they call it imaginary numbers is because in physics, anytime you have an I in your answer, means you cannot measure that, right? So and in physics, you have a lot of I's. You can't measure whatever they're looking at, but you can still use that quantity to find things that are measurable. Okay, so you can see if B is equal to 0, then you're all the real numbers right here, because this is 0 and it's pure real. If A is equal to 0, then it's purely imaginary. So we can draw on here to designate this on a complex plane. So we can put a complex plane here, and this is the real part of Z, and this is the imaginary part of Z. And so if we look at this point right here, one point on this two-dimensional complex plane, where this is A, and this right here is B. So this is that complex number we have right there. Okay, we can also define something called the complex conjugate. Complex conjugate. We're going to designate it as a star, Z star. And what you do is every place in your Z where you have an I, you just replace it with -I. So all you do is replace all of your I's with -I. So in this case, Z star would just be A minus IB. Over here, if I drew it on my complex plane, it would just be the mirror image down here. So there would be Z star. Okay, so we've got this. Now you notice right here, since we have Z equals A plus IB, if I were to add these two together, add Z plus Z star, well, the IBs drop out and we just get 2A, and we called A the real part of Z, so this is twice the real part of Z, or the real part of Z is just Z plus Z star divided by 2. So if you want to get the real part of Z, add it with this complex conjugate and divide by 2, or it's just the part that doesn't have the I in it. Also, if we were to subtract these two, say z minus z star, the a's would drop out, and ib minus a minus ib is 2ib. And b, we said, was the imaginary part of z. So this is 2I times the imaginary part of z, or the imaginary part of z is z minus z star over 2I. 2I. Okay, suppose we multiply z times z star. Z times z star. Well, that's a plus ib times a minus ib, which is a squared plus minus ib plus, this times this is minus iab. This times this is plus iab. And then this times this. Well, minus times a plus is a minus, but I squared is another minus, so this is always going to be plus. And we just get b squared. Well, these two cancel out. So z star is a squared plus b squared. And you can see that this is always real. Always real. There's no i's in it. And always positive. Always positive. Okay, and we'll call this right here, z star. It looks like we'll just call it the magnitude of z squared. And so if I just take the square root of both sides here, we get the magnitude of z is equal to the square root of a squared plus b squared. Okay, well, if we look at our picture over here, the square root of a squared plus b squared is this length right there. And so this length here is the magnitude of z. Magnitude of z. So it's the length from that point to the origin. So if you have two complex numbers and you want to know which one is larger in magnitude, just find the distance to the origin. Whichever one has the bigger distance is the larger number. Okay, and so another way we could write this as the magnitude of z is the square root of a squared. Well, a we said was the real part of z squared plus the imaginary part of z squared. So there's another way we could have written out this right here. Well, we can also define something over here, an angle. Let's call this angle theta, because we can also specify this point instead of rectangular coordinates. This is like an x and a y right here, a and b. We could have also signified it in polar coordinates, which usually you signify it by a radius, which is a magnitude of z, and an angle. Well, we can see from, say, this triangle right here that the cosine of theta is a over z. So we can see that the cosine of theta is equal to a over the magnitude of z. Or a is equal to the magnitude of z cosine theta. Likewise, the sine of theta is b over z, opposite over hypotenuse. And so we can say sine of theta is equal to b all over the magnitude of z. Or B, we can write as the magnitude of Z sine theta. So now I can take my A and B from right here and plug it right back into our definition of Z. So we get Z is equal to A, which is the magnitude of Z cosine theta, plus I times B, which is the magnitude of Z sine theta. Or I can pull out the magnitude of Z, and we end up with cosine theta plus I sine theta. Okay, there's one way we could write it, but there's a more compact way of writing this right here. Now, if you look at the cosine, let's say the cosine theta, right here, you can write this as an infinite series right here. If you look at the cosine theta, what is it? It's like 1 minus theta squared all over 2 factorial plus theta to the 4th over 4 factorial plus, minus theta to the 6 over 6 factorial plus dot, 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 dot. Again, if you look at the cosine theta, it first starts out at 1, and then it goes down as a inverted. If you just look at that much of it, it's just 1 minus a parabola. A parabola shifted up by 1, flipped. And then you're adding theta to the 4th, so that gives you this. Then you're subtracting theta to the 6th, and that gives you that. Adding theta to the 8th, and it just keeps going on. If you go on forever, you get the cosine of theta. Also, the sine of theta, we could write that. That has all the odd powers right here, which is theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial minus theta to the 7th over 7 factorial plus dot, 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 dot. Again, if we look at the sine of theta, you first have like y equals x, which is there, theta term. Then you're subtracting off the cube term. Well, there's the cube term. Then you're adding the 5th term. It goes like that. Subtracting the 7th term, and if you keep going on and on forever, you get the perfect sine theta right there. And then I just want to put one other one here, which is e to the x. That's just 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot, 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 dot. Okay, just wanted to look at those three right there. Because what I'd like to do is, suppose I replace all of my x's here with I theta. That is, what is e to the I theta? Well, every place I see an x, put in an I theta. So you got 1 plus I theta plus I theta squared over 2 factorial. I theta squared over 2 factorial plus I theta cubed over 3 factorial plus I theta to the 4th over 4 factorial plus I theta to the 5 over 5 factorial plus dot, 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 dot. Well, I can pull this I out right here. I squared is minus 1. So if I pull that out, it's just minus 1. I cubed is minus 1 times I, so that's just minus I. So this is minus I. I to the 4th is back to 1 again. So that's back to 1. I to the 5th is back to I. You're just going to keep repeating yourselves. It's 1I minus 1 minus I. 1I minus I. 1i minus 1 minus I. So this one is 1, this one's I, and so on, right there. Okay, so now what I'm going to do is I'm going to factor out all the ones that don't have the I in them. So if we factor out first the ones that don't have the I, you get 1. This one doesn't have an I in it because this came out to be just minus 1. So this is minus theta squared over 2 factorial. This one over here is just 1, so that's plus theta to the 4th over 4 factorial. And I would have had the next one right here would have been a minus theta to the 6th over 6 factorial plus dot, 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 dot. And then all the ones that have the I in it, I'll pull out the I. This one has an I, just theta. This one has a minus I, so we have a minus, pulled out the I, theta cubed over 3 factorial. This one has an I, so I just pull it out, and it's theta to the 5th over 5 factorial plus theta to the 5th over 5 factorial minus dot, 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 dot. Okay, well, you'll notice this looks exactly like this. This is just the cosine. So we have e to the I theta is equal to cosine theta plus I, and that is the same thing as this, which is just the sine of theta. Okay, some call this the most important equation in all of math. It would ties algebra to trig, but it takes a complex number to do that. Okay, well, if we come back to here, looks like I can write all of this as just e to the I theta. So we can write our complex number as the magnitude times e to the I theta. So that's just as good a notation as a plus IB. It's just as good. You notice from right here, if we were to say what is e to the I pi over 2? Well, if you just plug in pi over 2, cosine pi over 2 is 0. Sine of pi over 2 is 1. So this is just I. Right here. So you notice every time we come back to our complex plane, every time we multiply by I, all we're really doing is moving it over by pi over 2. So you'll notice way back over here, if we start right here at 1, multiply it by I, it really just brought me up to here, which put it at I. Then we multiplied it again, it came over here to minus 1, then minus I, then back to 1. I minus 1 minus I 1. And so that's all you're doing. When you're multiplying by I, you're just rotating it around this complex plane by 90 degrees. What about e to the pi, I pi? Well, this cosine of pi is minus 1, that's 0, so this is just minus 1. So this is an integer, it's real, even though we have two irrational numbers with an I in there, it's just minus 1. Suppose we wanted to know what I to the ith power is. Is that real or is that complex? Well, since I right here is just this, it's e to the I pi over 2, so that's the first I, and then you're just taking it to the ith power. Well, with properties of exponents, you just multiply that through, and so that's just e to the minus pi over 2, which is a real number. It's around 0.2. So there's your I to the ith power. Right here. What is the magnitude of this number right here? The magnitude of e to the I theta. When we write the two lines in there, that means you're taking the square root. So when we put this in there, you're taking the square root of z times z star. So this is just the square root of z star. Okay, so if this is just the square root of this, e to the I theta times its complex conjugate, e to the minus I theta. E to the I theta times e to the minus I theta, you just add their exponents. I theta minus I theta is 0. This is e to the 0, which is 1. The square root of 1 is 1. So this is just 1 right here. So this thing just has a magnitude of 1. It just tells you your phase as you're going around. What if you have something like e to the, instead of theta, what if it was changing with time? Usually you have theta equals omega t right here when you're going in a circle. What if we have e to the I omega t? So what is that doing right there? We're going to see that a lot in quantum mechanics. What you have is this point is just going around right here. It's not getting any, the magnitude isn't changing, it's just orbiting around, going around like this. So it's going from 1, 0 up to 0i to minus 1, 0 to, and so on as it just keeps going around right here. That's all it's doing. Okay. Well, what if we have something like 1 over z right here? How do we bring that up to the numerator? Well, what we do is we multiply the top and bottom by its complex conjugate. Because this now is real, and so this becomes z star all over the magnitude of z squared. So now we've brought the complex part up. Just to give you an example, what if we just had something like 1 over I? Well, what do? We multiply top and bottom by the complex conjugate. The complex conjugate would be minus I. Minus I. Minus I times I is just 1. So the denominator is just 1 and the numerator is minus I. So that's just minus I. So when you take 1 over I, when you bring it up to the top, it just changes the sign. It would do the same if you took it down too. What if we had something like 1 all over 3 plus 4i? Again, we would multiply top and bottom by the complex conjugate, which would be 3 minus 4i, 3 minus 4i. This times this, it's always the first number squared plus the second number squared. Plus, it's always. So that's 9 plus 16, which is 25. And the numerator would still stay as 3 minus 4i, or since I want to write it in the form a plus ib, it'd be 3 over 25 minus I, 4 over 25. Right there. So there's how you turn that, flip that right there. If we wanted to find the magnitude of this right here, then remember, this is, if I wanted to find the magnitude of this 1 over that, I would multiply this by its complex conjugate and take the square root. So the magnitude of 1 all over 3 plus 4i since I already brought it up to this, is just the magnitude of this, which is the square root of this term squared plus this term squared. So that's 9 over 25 squared plus 16 over 25 squared. Well, the 9 and the 16 is 25, so it's 25 over 25 squared, which is 1 over 25, and then take the square root, it's just 1/5. Right there. Now we could have, if we didn't want to, we could have just said, what is the magnitude of this number? And said, because this happens to also be 1 over 3 plus 4i, and we know that this is this one right here is a fifth, because it's the square root of 9 and 16 is 25, so this would just be 1/5 also. Well, because of this right here, you notice if we were to take the complex conjugate of this line right here, well, let me rewrite it for a minute. We got e to the I theta equals cosine theta plus I sine theta. Now, if I replace all of my i's with minus i's, that's also true. E to the minus I theta is equal to the cosine theta minus I sine theta. And if I just add these two together, these two drop out, and we just get 2 cosines on this side, 2 cosine theta, and on this side, I get this plus this, e to the I theta plus e to the minus I theta. And so it looks like if we divide by 2, the cosine theta is just e to the I theta plus e to the minus I theta all over 2. Or, if we were to have subtracted them, then the cosine would have left and we would have doubled this one. So if we subtract them, this minus this, e to the I theta minus e to the minus I theta, these two would drop out and we'd get 2i sine theta, or sine theta, I can write as e to the I theta minus e to the minus I theta all over 2i. So, and if I wanted to write the tangent, I could divide them. If I wanted to get the secant, I could have flipped this one. If I wanted the cosecant, I could get all the trig functions. So if you hate trig, but you like algebra, you can make it so you never have to see a trig function again. Switch all of your trig functions into these. You could derive all the trig identities and that you could use right here. A lot of times we like to use e to the i's in physics rather than the trig functions because it's so easy to take the derivative of e to the power of x. It's so much easier to take integrate, and there's only one of them. There's just e. You don't have to worry about the secant and the cosecant and the cotangent. They're all just e's right there. Okay, so again, you could just get rid of trig right here and just use e's all the time. And, you could even prove that if you squared this and squared this and add them, you better get 1 right here, because we know cos squared plus sine squared equals 1. Now, you notice on the last lecture, when we did particles versus waves, we said that there was some sort of a wave coming here, and we said the definition of the wave, the intensity at a certain point, due to hole number 1, we said was given by this right here. And we said the intensity given by hole number 2 was given by this, where h is the height that you're going up and down. And we said when you open up both holes, you had to add the h's together and then find the magnitude squared. Well, I left off some steps here because I wanted to say something about that first. If we were to look at a point right here, forget about 2, just 1 is open right here. And this point right here is just going up and down, right there. The x position isn't changing, it's just changing in time. And so we could have said, instead, we could have said y1 is it's just going up and down with an amplitude of h1, so it'd just be h1 cosine omega t. We could have put a phase shift, but I'll assume that this one doesn't have this one right here, one doesn't have a phase shift in it. So this is what it looks like right here. But you notice, didn't we just say that e to the I theta is equal to the cosine theta plus I sine theta? What if we just wanted to look at the real part? Remember, whatever we measure is always the real part. What is the real part? The real part of e to the I theta. So if we just write the real part of e to the I theta, well, that's just cosine theta. So let's just deal in the real part for a minute. It doesn't matter, we can keep it, but let's just, since we're measuring real stuff right here, we're just going to look at the real part. So that means that y1 is just h1, maybe I'll just keep it in there, times the real part of, now it's not e to the I theta, theta is omega t, it'd be the real part of e to the I omega t. So that's what y1 would be right here. Now, if we wanted to find the magnitude of this right here, because this is what y1 is, intensity of 1 is the magnitude of this. So it's actually the magnitude of y1 squared, which is this times its complex conjugate right here. So it's h1 times the real part of e to the I omega t times its complex conjugate, which is h1. H1 is a real number, so I don't have to put a star there, times the real part of e to the minus I omega t. Well, when I multiply these two together, h1 and h1, that's just h1 squared. And then this, e to the I omega t times e to the minus I omega t, you just add their exponents. That's e to the 0, which is 1. And so that's always real. That's why I said I didn't even need this. It's always going to be real. And so you just got h1 squared. I could have put this in there. And that's why we had this up here. I could do the same thing with 2. y2 is going to be h2. But it's going to be phase shifted. It's not going to have exactly the same phase. Oops, sorry, right here. The phase from that won't be the same as the phase from this one. So we'll just say y2 is h2 cosine omega t plus some phase shift, delta. Okay, so that means I2 is going to be y2 squared, which is this times its complex conjugate right here. Remember, we can also write this as h2 times the real part, h2 of, what was it now? It's going to be e to the I omega t plus delta. Omega t plus delta. Okay, so now when I multiply this times its complex conjugate, you're going to get h2 times the real part of e to the I omega t plus delta times another h2 times the real part of e to the minus I omega t plus delta. Okay, and now when we multiply these through, this and this, you add their exponents, they just cancel out. So this is gone with that, and you get h2 squared. Okay, and then the last case is what happens when they're both open right here. What did we do? We had to add them two together up. So I1 well, let's first get the total height right here. The y total would be y1 plus y2. It would be the sum of y1 plus y2. So it would be h1 cosine omega t plus h2 cosine omega t plus delta. Okay, and now I can write them in terms of exponentials. Assuming they're all the real, I'll just take in the real part of this. We can say y is equal to the real part of, it's just h1 e to the I omega t plus h2 e to the I omega t plus delta. Okay, and now if we wanted to find out what the intensity is, I have to multiply this by its complex conjugate. So I1, 2. If we multiply this by its complex conjugate, I'm going to leave out the real part here. We get h1 e to the I omega t plus h2 e to the I omega t plus delta times its complex conjugate. h1 e to the minus I omega t plus h2 e to the minus I omega t plus delta. Okay, so if we multiply these two together, we can first get this term times this term. The exponentials drop out because you add their exponents. That gives you 0. You just get h1 squared. h1 squared is just I1. So this gives me I1. The last term, this times this. This term and this term multiplied together just gives me 1. So they're gone. So I just get h2 squared, or just plus I2. Now it's the cross term right here. So what do we have to do? I have to multiply these two together. So I get plus h1, h2, e to the I omega t times this right here. What do? We add their exponents. So you get I omega t minus I omega t minus I delta. The I omega t's drop out when you multiply these two, and you just get e to the minus I delta. And then I have to worry about these two right here. These two gives me a plus h1, h2. And now when I multiply these two exponentials, the e to the I omega t and e to the minus omega t are drop out, and this is just e to the I delta. Okay, and now one last step here. This is I1 plus I2. And then I can factor out the h1, h2 out of these two terms, and in place of h1, I'll put the square root of I1, square root of I2. Since they're real, we can just say that. And now what are we left with? We're left with e to the I delta plus e to the minus I delta. So this is e to the I delta plus e to the minus I delta. And you remember from over here, e to something, e to the I delta plus e to the minus I delta, would just bring that over to here. It's just 2 cosine delta. Just put theta in for delta. That would be e to the I delta plus e to the minus I delta is 2 cosine delta. So matter of fact, I can just make this whole thing right here 2 cosine delta. 2 cosine delta. And you'll notice that's exactly what I had up here. So I just went over this before, but I didn't say where that interference term came from. It came from the cross terms when you multiplied it by its complex conjugate. Right here. So this is just to give you a little bit of practice on complex numbers. Now, there's nothing much else to complex numbers right here. But we'll be seeing a lot of e to the I stuff.